Welcome back to the channel. Today we are looking at one of the most significant shifts in industrial engineering of the 21st century. We are talking about the moment metallurgy finally caught up with our imagination. For decades, the design of jet engines, gas turbines, and rocket propulsion systems was constrained not by physics, but by the limitations of a crucible. We are talking about superalloys. These are the high-performance nickel, cobalt, and iron-based metals capable of withstanding the hellish temperatures of combustion. Historically, they were a nightmare to work with. They were notoriously difficult to machine, they cracked if you looked at them wrong during welding, and they were limited to shapes that you could pour into a mold. But in 2024 and 2025, the narrative changed. We have moved past the era of merely adapting old casting alloys for 3D printers. We have entered the age of printable superalloys. These are materials designed at the atomic level, specifically for the rapid heating and cooling cycles of a laser beam. We are seeing breakthroughs like NASA's GRX 810 and novel heat treatments that have shattered previous performance ceilings, offering components that are 1,000 times more durable than their traditionally manufactured counterparts. So let's break down this material revolution, the science behind it, and why it changes everything for aerospace and energy. To understand why this is such a big deal, we have to understand the problem with traditional superalloys, like Inconel 738 or MAR-M 247. These materials were never designed to be welded. When you subject them to the intense, localized heat of a laser in laser powder bed fusion, they suffer from something called hot cracking, or strain age cracking. As the metal solidifies rapidly, it leaves behind microscopic fissures. In a flight-critical part, that is a catastrophe waiting to happen. For years, the industry compromised by using lower-performance alloys that were weldable, like Inconel 718. But that compromise is effectively dead. The crown jewel of this new era is undoubtedly GRX 810, an oxide dispersion-strengthened alloy developed by NASA. Now, ODS alloys have been the holy grail of high-temperature metallurgy for a long time. They contain tiny, nanoscale ceramic particles dispersed throughout the metal matrix. These particles act like pins holding the grain boundaries of the metal in place, preventing the metal from deforming or creeping under heat and stress. The problem was that making these alloys used to require expensive, slow mechanical ball milling processes that you simply could not scale for complex shapes. NASA changed the game by combining computational modeling with additive manufacturing. They used thermodynamic modeling to find the precise alloy composition that would allow nanoscale yttrium oxide particles to form in situ, or right there inside the printer, during the process. The result is a printable alloy that can withstand temperatures over 2,000 degrees Fahrenheit. Compared to current state-of-the-art additive superalloys, GRX 810 is twice as strong, twice as resistant to oxidation, and astonishingly 1,000 times more durable in creep rupture tests. This isn't just a lab experiment anymore. In 2024, NASA licensed this to major players like Carpenter Technology and Elementum 3D, and ton-scale quantities of the powder are already moving through the supply chain. But the revolution isn't just about nickel. We are also seeing a surge in high-entropy alloys, or HEAs. Standard alloys usually have one base element, like nickel, with small sprinkles of other things. HEAs mix 5 or more elements, like aluminum, cobalt, chromium, iron, and nickel, in roughly equal proportions. This creates what material scientists call the cocktail effect. This complex mixture creates a severely distorted crystal lattice that naturally stops dislocations from moving, leading to exceptional strength and fracture toughness, even at cryogenic temperatures. Surprisingly, these complex chaotic lattices print very well because the sluggish diffusion of atoms prevents brittle phases from forming. Then there is the work coming out of Sandia National Laboratories and Ames National Laboratory. They developed a supersolar alloy made of 42% aluminum, 25% titanium, and a mix of niobium, zirconium, molybdenum, and tantalum. Here is the mind-bending part. This alloy is actually stronger at 800 degrees Celsius than it is at room temperature. This is counterintuitive, but it comes from a unique precipitation hardening behavior. This material is poised to revolutionize concentrated solar power plants and nuclear reactors, where thermal efficiency is directly tied to how hot you can run the system. Now let's shift gears to the process itself, because having the powder is only step one. You need to shape it. Laser powder bed fusion, or LPBF, remains the gold standard for critical rotating parts, but the technology has matured from a black box art to a precise science. The latest machines feature multi-laser systems, some with 12 or more lasers scanning simultaneously, which drastically reduces print times. We also have beam shaping technology. Engineers can now switch the laser from a Gaussian spot for fine detail to a ring mode beam for fast bulk melting on the fly. This reduces spatter and porosity, which are the enemies of superalloys. Artificial intelligence has also become standard. Cameras monitor the melt pool in real time. In some advanced systems, the AI can detect a defect in one layer and adjust the laser power in the next layer to heal it, effectively creating a self-healing manufacturing process. However, the biggest disruption might be in binder jetting. For years, binder jetting, where a printhead deposits a glue-like binder onto powder, was considered useless for superalloys because it was hard to get high density during the sintering step. That has changed. Companies like Desktop Metal and HP have cracked the code on sinter-friendly binder chemistries and shrinkage compensation. Binder jetting is roughly 100 times faster than laser printing and significantly cheaper. By printing a part 20% larger than needed and predicting exactly how it will shrink in the furnace, manufacturers can now achieve aerospace-grade densities of over 99%. This opens the door to using superalloys in automotive turbochargers and industrial pumps, not just million-dollar rocket engines. We also cannot forget electron beam melting, or EBM. Because this process happens in a vacuum at high temperatures, usually over 800 degrees Celsius, the part is essentially heat-treated while it is being printed. This reduces residual stress, making EBM the preferred method for printing crack-sensitive titanium aluminides used in the low-pressure turbine blades of massive engines like the GE9X. This leads us to one of the most profound realizations of the last 2 years. Printing is not just shaping, it is heat treating. The cooling rates in additive manufacturing can reach 1 million degrees Celsius per second. This creates unique microstructures that cannot be replicated by casting. We are entering the era of digital metallurgy. In a cast turbine blade, engineers spend millions to grow a single crystal structure to eliminate grain boundaries, which are the weak points where breaks begin. In additive manufacturing, we are learning to print the grain structures we want. By manipulating the laser scan strategy, engineers can force grains to grow in specific directions. Imagine a rocket nozzle, printed with columnar grains running vertically to resist thermal stress, transitioning to random equiaxed grains in the mounting flange for better strength in all directions. It is total control. But there is a catch. Printed superalloys often have a fine-grained structure, which is great for strength but bad for high-temperature creep. This is where MIT's directional recrystallization comes in. This is a post-print heat treatment that acts like a magic wand for microstructure. A 3D printed rod is passed through an induction coil at a very precise speed and temperature. This thermal gradient sweeps through the material, causing the chaotic, mangled spaghetti of fine grains to snap into alignment, forming massive, single crystal-like grains. This technique could allow 3D printed blades to finally match the creep performance of single crystal castings. Of course, no superalloy part comes out of the printer ready for flight. Post-processing is the hidden half of the equation. We have hot isostatic pressing, or HIP, which uses high pressure to crush internal pores. New high-pressure heat treatment units combine this with rapid quenching in one cycle, streamlining the supply chain. Then there is the challenge of surface finish. The greatest advantage of printing superalloys is the ability to create complex internal cooling channels, like the capillaries in a lung, inside a turbine blade. But if those channels are rough, airflow suffers. The industry is using abrasive flow machining, forcing a diamond grit putty through the channels to polish them. We also have new chemical polishing techniques that can wash the interior of a heat exchanger, reducing surface roughness by up to 80%. On the outside, techniques like plasma additive layer manufacture smoothing use plasma pulses to remelt just the outermost microns of the surface, creating a mirror finish that improves fatigue life. So where's this actually being used? The hype phase is over, we are in the deployment phase. NASA and Elementum 3D have conducted hot fire tests of rocket engine components made from GRX 810. These injectors and nozzles survive durations and temperatures that would have melted Inconel 718. Because they can print these parts as a single piece, they eliminate the O-rings and bolted joints that are common failure points in rocket engines. In the energy sector, as the world shifts to green hydrogen, gas turbines need to run hotter and handle faster flame speeds. Siemens Energy and GE Vernova are using printed superalloy fuel injectors with micromixer designs. These act like complex lattices that mix hydrogen and air so rapidly that the flame cannot flash back, a design only possible with 3D printing. Even Formula One is on board. Teams are printing Inconel exhaust headers that are 20% lighter than bent steel tubes, with walls just half a millimeter thick to dissipate heat rapidly. The final hurdle, as always, is certification. You can print a miracle alloy, but if the FAA does not certify it, it does not fly. The National Center for Advanced Materials Performance is creating public databases for additive superalloys to standardize the recipes. But the future is the digital twin. Instead of destructively testing every 10th part, manufacturers are recording terabytes of data during the print. If the data shows that every voxel was melted within the allowable window, the part is deemed airworthy. This concept of born qualified parts is critical for mass production. Looking ahead to 2030, we see the rise of future foundries. We are looking at autonomous production, where robots move parts from printers to depowdering stations and furnaces, with zero human intervention. It is also a sustainability win. The buy-to-fly ratio, which is the amount of raw material bought versus what ends up in the air, drops from 10:1 with machining, down to near 1:1 with printing. Plus, we can now repair turbine blades by printing new material directly onto worn surfaces. We are witnessing the end of the design for manufacture era, and the beginning of the manufacture for design era. Superalloys have been tamed by the laser. With breakthroughs like GRX 810 and industrial-scale binder jetting, the next generation of engines will be lighter, rockets will be more reusable, and power plants will be more efficient. The age of printed superalloys has arrived, and it is built to withstand the heat. Thanks for listening, and stay tuned for the next deep dive.